Okay, guys, here we go into part 2 of section 4.1. So we finished up here talking about the two forms of quadratic functions that we're going to be using. Standard form, which is going to come later in 4.2, but then vertex form. So what I wanted to do with you now is run through a few kind of sample graphs of what some of these might look like here. Let's take a look at our first example here. So we did our parent graph of y equals x squared a few slides ago. It looked something like this, and we said that every parabola we're going to graph is going to be built off of that one. And what I'm hoping now we're going to find is that all of the things that we talked about back in chapter 2 about translating functions are going to apply here. So what's going on here, guys? Our first example is y is equal to 3x squared. Now this is the same normal function that we deal with, x squared, but it's being multiplied by a 3 out in front. And if you guys remember what that means, to take any function and multiply it by an a value bigger than 1, like 3, that's what we call a vertical stretch. By I forgot a t there, by a factor of 3. This graph is going to get taller. So what I drew here for you in this graph, or I stole it from my calculator, is that dotted line of your parent graph. That one right there is the graph of y equals x squared. Your graph now is going to be 3 times as tall as that. Now it's still never a bad idea, just as we're getting started, to make ourselves kind of a quick little table, and this won't take as long as the last one, guys. I'm going to put in, let's see here. I'm going to put in -1, 0, and +1. Let's see what happens. And you got to pay attention to order of operations. When x is -1, you're going to take -1 and square it first to get 1. Times 3 gives you a y value of 3. So this graph is going to pass through the point -1, 3 right there. 0 is fun. Let's put a 0 in there. 0 squared is 0 times 3 is still 0. So this graph still passes through the origin. But now when we put in +1, 1 squared is 1 times 3, we get 3 again. And I'm wondering if you guys can look at those 3 purple dots now and realize what I'm talking about. This graph is still going to be a parabola. It's just going to be taller than the original, which makes it appear skinnier. Just for fun, let's throw a 2 in there, although you'll see why I didn't originally. 2 squared is 4. 4 times 3 is 12. Shoot, 212, and I'm up off my graph already. It's way the heck up here somewhere. So here we go, guys. When I try to connect this, you'll see what I was talking about a while ago. This is a pretty darn skinny parabola. That's what happens, guys. You get a skinny parabola when your a value has an absolute value that is greater than 1. And that's what happened here. Our a was 3, and that means we have a skinny parabola. Although really, the reason it looks skinny is because it's actually tall. Okay, so that's a transformation right there, one translation that we should know. That 3 makes it taller there. Okay, now I'm throwing 2 wrinkles at you here with example B. Y is equal to -1/3 times x squared. Okay, if putting a 3 out in front made our graph taller, then putting an a value less than 1, like 1/3, is going to have the opposite effect. That's going to push the graph down and make it appear wider than it normally would. However, there's also a negative out in front of the whole thing. And if you guys remember, what that negative does is it flips your graph over the x-axis. And now for the first time, we're going to get a parabola here now that is going to open downward. So that negative right there tells us that it opens downward. That's good to know. And the fact, let me write this here, that the absolute value of a is less than 1, that means that we have a wide parabola, although really it's because we have a short one that it just appears wide. So this table might be even less fun for you guys than the last one was. But if I were to put in -1, 0, and 1, let's see what happens. -1 gets squared to make +1. -1/3 times +1 is -1/3. So we're beginning this graph at -1, and then -1/3 is maybe right about there. If we put in a 0 now, 0 squared is 0 times -1/3. We're still hitting the origin here at 0, 0. And if we put in +1, +1 squared is 1 times -1/3 is -1/3 again. 1 negative 1/3. So maybe you guys can see what's happening already through those 3 dots. This parabola is opening downward, and it looks like it's going to be wider than normal. Just for fun, this time I'm going to throw in a 3, and you might be able to tell the reason why is because there's a 1/3 there for our coefficient. Okay, 3 squared is 9, 1/3 of 9 is 3, and the opposite of that is negative 3. So we're going to get the point 3, negative 3. Okay, and now I'm getting a sense for what this graph looks like over here on the right. And of course, it'll do the same thing over here on the left because all parabolas are symmetric with respect to, in these cases so far, just the y-axis. Okay, so those are 2 variations on the parent graph of a quadratic function. Let's keep going and let's do a few more right here. And I'm hoping you guys kind of knew what was coming here because this is different than what we did on the last couple of examples, but it should feel similar to what we did back in chapter 2. What's happening now in example C? Y is equal to x squared, but then there's a minus 5 at the end of all that. And what does it do to any function to put a minus 5 at the very end of it? That is going to shift your function down 5 units. So this one is going to shift down 5. Now what I think that tells me is that instead of the vertex being right here at 0, 0, I'm actually going to move that point 1, 2, 3, 4, 5 units down. And I think my vertex is actually at the point 0, negative 5. Now, of course, we could check that. Let's make this same table of values, guys, real quick. Negative 1, 0, 1, and let's see what we get. Negative 1 squared is 1. 1 minus 5 is negative 4. So negative 1, negative 4 is our first solution. 0, we'll square that to get 0. Minus 5 is negative 5. That's the point I already had right here. And putting in a 1, 1 squared is 1, minus 5 is negative 4. Okay, that's a parabola that looks like it's opening up. This is what a normal width parabola looks like. If you guys noticed, from the vertex, it's right 1, up 1, left 1, up 1. That's what a quote-unquote normal parabola should be doing. Okay, I don't actually want those in my graph right here. Let me get rid of that. But anywho, all right, and that's what we've got. And this graph is just going to open up and look something like this. So putting a minus 5 at the end of your function simply shifts it down 5 units. And now the last one of these I wanted to do with you, what does it do to a function to put a minus 5 inside the parentheses? That one right there, you guys, is a horizontal shift. And horizontal shifts, to me anyway, are always the opposite of what you would expect. A minus 5 kind of seems to suggest left, but we're actually going to go right 5 units here. Now, if you don't believe me on that, the table will tell you if you're right or wrong. Let's see. Negative 1, 0, and 1. So let's plot some points here. Let's put in a negative 1. Negative 1 minus 5 is negative 6. Oh boy. And then negative 6 squared is 36. Now that's correct, but I'm not graphing that. Maybe this was the wrong table. Putting in a 0, almost as bad. 0 minus 5 is negative 5. Negative 5 squared is 25. Not graphing that. 1 minus 5 is negative 4. Negative 4 is... Okay, so these values are correct, but maybe we should have been a little bit smarter about the x values that we're putting in. All of our graphs so far have been symmetric right down the y-axis right there. This point has been the vertex at 0, negative 5 in that case. However, guys, since we're now shifting right 5 units, I have a hunch that my axis of symmetry is actually right over here at the line x equals 5. So maybe I should have put a 5 in this table in the middle, and how about a 4 before that and a 6 after that? Let's see if we get more graphable points this way. So plugging in a 4, 4 minus 5 is negative 1. Negative 1 squared is 1. Oh, that's not that bad. So 4, 1. Got it. Let's plug in a 5 now. Oh, this is fun. 5 minus 5 is 0. 0 squared is 0. And let's put in our 6 now. 6 minus 5 is 1. 1 squared is 1. Oh, yeah. So now those are the 3 dots that I was looking for. This is a parabola that opens up. It's a normal parabola. But this one is being shifted 5 units to the right, and I can kind of see that from the values in the table. All right, so those 4 examples are meant to show you guys here what it looks like when you're doing a couple of different transformations, but one at a time. Now let's take a look at this guy right here. And this is kind of the gateway into some of the harder problems that we're going to be doing. All right, guys, this is a parabola with all the fixins going on right here. We have an A value here of -2. H is the value that gets subtracted from x. Now I see a +1 there. That means that h is actually -1. It's always going to be the opposite of whatever this number here is. And k is the number that's added at the very end. K is 4. So with those 3 pieces of information, we're going to be able to figure out everything we need here. And hopefully you guys can answer these for yourself before you hear me say it. What direction does this parabola open? That's determined by the value of a. And since a is negative, our parabola opens downward. Next question, is this parabola wide or skinny or normal? That is determined also by the value of a here, and the absolute value of a is going to be +2, which is greater than 1, and that means that our graph is being stretched vertically. It means that it's tall, so we're actually dealing now with a skinny parabola, and I should say because it's actually taller than normal. And then the vertex of this parabola is located at this ordered pair right here. H is -1 and K is 4. So with all of that information that we have there in red, it's actually not that hard to come up with this graph. We start at the vertex, which is -1, +4, located right there. And it wouldn't be a terrible idea to check this, and maybe not as hard as you think. When we put in -1, y should equal 4. Let's try it. So x is -1. -1 plus 1 is 0. 0 squared is 0. Times -2 is 0. Plus 4 gets us the 4 here that we were looking for. All that worked out, so we're in pretty good shape. And then from there, what we would probably do is take advantage of the fact that this thing opens downward and know that it's down, it's skinny, and it's being stretched, but it's still probably a good idea for us to come up with a few more values right here. Now, I'm going to try to get you guys in this habit. We already know one ordered pair right here. -1, 4 is our vertex, and you'll notice I'm putting that right in the middle of my table. Above that, I'm going to put in some lesser values. Which way? Sure. We'll go -2, -3, and below that I'll put some greater values than -1. How about 0 and 1? And if we do this right, with the vertex in the middle of the table, you should start to see something cool. Okay, guys, I'm going to put in this -3 here for x back into the original. -3 plus 1 is -2. Squared, -2 squared is 4. Times -2 is -8, and -8 plus 4 is going to be -4. So -3, -4 is the next solution that we've come up with. Okay, now let's go to the next one. Let's put in -2. -2 plus 1 is -1, squared is 1. Times -2 is -2, and -2 plus 4 is 2. -2, +2. That's where we're at so far. 0 is usually an easy number to work with. Let's try it. 0 plus 1 is 1. Squared is 1. Times -2 is -2. Plus 4 is 2. So we get the point 0, 2 right there. And now let's put in this last value here of 1. 1 plus 1 is 2. Times itself is 4. Times -2 is -8. And -8 plus 4 is -4. So 1, -4 is the 5th solution we came up with. And before I go ahead and just connect the dots, I want you guys to realize what's happening in this table. And everybody, this is not a coincidence. Every parabola, if you do it right, is going to do this. The vertex should be located in the middle of the table, which means that this y value right here should be either your maximum or your minimum y value. And if you take a look at all of the values that we came up with in this column, 4 is the max. So I think on the next question, I'm going to ask you guys for this, the maximum value of this quadratic function is 4. Beyond that, check this out. There is symmetry, everybody, around the vertex. When you go 1 unit left and 1 unit right of -1, your y-coordinates are the same at 2. And the same thing happens when we go 2 left and 2 right. Your y-coordinates are both -4. If that doesn't happen in your table, you're probably doing something wrong. Maybe just making the table incorrectly with the wrong x values, but it could be a sign of a bigger problem. Okay, guys, let me go ahead and draw the rest of this parabola in, and the dots kind of tell me what I already knew a while ago. We knew that this parabola opens downward, and sure enough, it does. We knew that this parabola was skinnier or taller than average, and I don't know, it's kind of hard to see, but I think the purple graph that I came up with compared to the black outline, I think you can see it's just a little bit skinnier, and we thought that the vertex was going to be located at -1, 4. Sure enough, that's your vertex right there. So all right, everybody, that's what it looks like when you try to put all the hard stuff here together. So now that I did all that, these next 2 problems are going to go pretty easy. I've got 2 more. If I was with you guys in class, I'd probably do this one with you and then have you do B on your own. So let's give it a go. So using vertex form, here we go. And you'll notice I've gone to y instead of f of x, but it's really the same thing. Okay, your vertex is the ordered pair h, k. H is the number being subtracted from x, which in this case is actually a -2. K is the number that gets added at the end, which is a +3. So okay, there's our vertex. Now this axis of symmetry we haven't really talked about before right here, but very simply, guys, let me give you a quick little formula right here. It's just x equals h. And h is the value we were just talking about here a second ago. Our h value in this problem is -2, so x equals -2 is our axis of symmetry. That's not really a question I needed to ask you here in 4.1. It's more of something we're going to talk about in the next section of 4.2. Okay. Maximum or minimum value? Well, way back on the first slide, we said that the maximum or minimum value is the y value of your vertex. And our vertex is the point -2, 3. This 3 right here, then, is either your max or min. Now, which one is it? Oh, and I didn't ask you this one here, guys, and I should have asked this question. That is determined by what direction this graph opens. Well, your a value right here is +1/2. That means that this graph opens up. And a parabola that opens upward like this does not have a maximum value. It keeps getting higher on both sides, but it does have a minimum value. So I'll go ahead and make clear we have a minimum value of 3. Now, I'm not going to ask you guys too much about domain and range. I'll come back to that after I come up with this graph. So let's take everything we've learned, or that we think we've learned anyway, and let's see if we can't put it all together. Our vertex is at the ordered pair -2, 3. So we're up here in the second quadrant. We believe that this graph opens upward. Our axis of symmetry, x equals -2, is a vertical line, just in case you guys forgot that from back in chapter 2. So sometimes we like to draw that. That's a good habit to get into there. And we think this thing should be opening upwards from there. So not a bad idea here, guys, to make a quick table of values, x and y. The vertex, which we think we've already found, should go in the middle of the table here. And I want to teach you guys a lesson right here that you might want to just hold off on for a second now and not do this just yet until I show you guys what it is that I'm going for here. If you're not real careful about this, you can get kind of messy here in a hurry. Let me show you what I mean. Normally, don't write this down, guys, I'd put a -1 right here for a value less than -2, but watch what happens when I do that. -1 plus 2 is 1, no problem. 1 squared is 1, but now when I go to multiply 1/2 times 1, I end up with a fraction here. And that's not wrong. 1/2 times 1 is 1/2, and 1/2 plus 3 is 3.5. Now this is not incorrect, but most people kind of like to avoid dealing with fractions if they can. So what I'm going to do instead is not put the -1 in there for x and actually go, let's see, a 2 to one side of that. I'm going to jump to 0 here. And if I do that, put a 0 here and maybe a +2 here, I think by jumping by 2's, I can avoid some of those fractions. Let's try it. Putting in a 0, we'll do that right up here, guys. All right. 0 plus 2 is 2. Squared is 4, and this is nicer now. Half of 4 is 2. 2 plus 3 is 5. So yeah, we were able to avoid that fraction here by jumping 2 units. Let's see what happens when we put in a 2 now. 2 plus 2 is 4. 4 squared is 16. Half of 16 is 8. 8 plus 3 is 11. Now shoot, that's going to be off my graph a little bit, but the point 211, I'm going to guess is maybe up here somewhere. What am I doing now? I'll put a -4 in down there, and we should start to see some symmetry here, everybody. When we put in a -4, -4 plus 2 is -2. Squared is 4. Half of 4 is 2. 2 plus 3, is 5 again. So -4, 5 gets us right there. That really shouldn't surprise us. And then we'll put in one more value here. How about -6? -6 plus 2 is -4. Squared is 16. Half of that is 8, and 8 plus 3 is 11. So again, I'm just guessing here, but -6, 11, probably right about there. So now let's go ahead and let's graph this parabola, guys, by connecting those 5 dots, and that's what this one looks like. Now, I said we'd come back and talk about domain and range. Domain is the set of all your x values in the function that will give you a real result. Well, guys, because of the arrows here and here, this graph is going to continue to spread to the right and off to the left. So your domain here is what we would call all real numbers. And there's a symbol we use for the set of all real numbers, guys. It looks like an 11, but then you make a big capital R out of that. So all real numbers. Range is the set of all y values. Now, are we going to cover all the way up towards infinity and all the way down towards -infinity with this function? No. This vertex right here, we said, is your minimum value. So what we're going to say here is that the range of this function is going to be all y values that are equal to 3, or, which is it, guys, higher or lower than 3. This graph goes up, but not down. So our range contains all y values that are greater than or equal to +3. Like I said, I'm not going to ask you that a ton, but that'll show up from time to time. Okay, let's do another example here. And as I said, if we were in class, I would have you guys do this one on your own, and then we'd come back and check. So maybe think about pausing the video right here, seeing if you can answer these 6 questions on your own, and then come back and see if you got it right. Okay, hopefully you did that. All right, first question, and I should have started with this one on the top. What direction does this one open? Well, what happens here, guys, is that number there, -5, is our a value. And when a is negative, this parabola opens downward. The vertex comes from the ordered pair HK. H is the number subtracted from x, which is 3. Even though this looks like a -3, this value is actually +3. K, the y-coordinate of your vertex, is this number here at the end, just the way it appears, so that's -1. So our vertex is the point 3, -1. The axis of symmetry, we said, is just the line x equals h. Here was our h value there, so x equals 3. The minimum or maximum value is the y-coordinate of the vertex, so that's going to be -1. And since this parabola opens downward, it's going to look like this. This point right here is which one of those, guys? A maximum or a minimum value up at the peak? That's a maximum value. This one doesn't have a minimum. And I'll come back to domain and range in just a second. So let's start graphing, guys, although we're going to have to do some work before too far here. Our vertex is the ordered pair 3, -1. So 3 to the right, 1 unit down. There we go. Our axis of symmetry is that vertical line, x equals 3. Looks like that. And now we probably better come up with a table here, although we might run out of room here sooner than you might think. I like to put my vertex in the middle of the table here, so that is going to be 3. Nope. There we go, 3 and -1. Now, since we don't have a fraction as a coefficient in front of this thing, I'm not too worried about what x values I'm going to put in. So let me go less than 3 by 1 to get 2. Greater than 3 is going to get me a 4. These two I think I can pull off. After that, it might get tough. Let's try putting in the 2 first. 2 minus 3 is -1. -1 squared is +1. And 1 times -5 is -5. Minus 1 is -6. So 2 -6 is one solution. You're going to see something similar now when we put in 4. 4 minus 3 is 1. 1 squared is 1 times -5 is -5. Minus 1 is -6. There's that symmetry that we were expecting to see. So we get the ordered pair 2, -6 for one solution, and then 4, -6 for another solution. Now what's going to get ugly is if I were to go to put a 1 and a 5 in right here. Now I promise you this will work. You might just not like where these points end up. Let's try it. If we put in 1, 1 minus 3 is -2. Squared is 4. -5 times that 4 is -20. Minus 1 is -21. We're not going to graph that. And the same thing would happen when you put the 5 in there. You'd end up with -21 as well. But the point should still be valid here, guys. There's the vertex. That -1 is the maximum value in this y column. And then there's symmetry around that point. That should happen every time you make your table. So I guess we just get 3 points on here, guys. But sure enough, we have a parabola that opens downward and is really, really skinny. And that's what I think we knew about this graph already. Real quick, what's your domain? Once again, you'll notice a pattern here. That is going to be the set of all real numbers. But the range now is going to be the set of all y values that, well, let's take a look at our vertex right here. We have a y value there of -1, and we said that was your maximum value. So all the y values that occur here are going to be less than or equal to that y value of -1. So those couple examples there, guys, really kind of illustrate what it is that we're doing here within this section. And the last one, I've got 2 of these, but I think I'm just going to do one with you here and then we'll be done. Write the equation of each quadratic function in vertex form. So what's going on here, guys? I've given you the vertex, which is at the point 3, 5, and then I've said that it passes through the point 5, 13. So since we're talking vertex form, let's write that out. Y is equal to A, and then in parentheses, x minus h, close it, square it, and then a plus k at the end. Now here's what I'm hoping you guys know. There are how many variables in this formula? Let's count them. 1, 2, 3, 4, 5. And how many values were given to you in this problem? 4. Now let's take a look at what we know. The vertex is always at the ordered pair hk, which means that 3 is your h value and 5 is your k value. Then any other point that's located on the parabola itself, those are your x value and your y value at a particular point. What we're missing here, guys, is the value of a. I didn't tell you that, but that's something that we can find algebraically. Notice there's 5 variables in this formula. 4 of them were given to you in this problem, all but 1, and we can solve if there's only 1 unknown. So here we go, guys. Let's fill in the 4 values we do know. At this random point, what's our y value? Right over here, 13, is equal to, we don't know what a is, and we're not supposed to, so don't panic. And then in parentheses, what goes in for x? That's this 5 right over here, minus, what is h? That's 3. So 5 minus 3, close it, square it, and then plus k, your k value right here, is 5. Now, it's a little messy, guys, but that's a one-variable equation now that I think we can solve. 13 is equal to, let's do a little math here in our heads. 5 minus 3 is 2. 2 squared is 4 times a is going to be 4a. And then there's a plus 5 just hanging out at the end of that. Okay, what are we doing now? We're going to subtract a 5 from both sides. I'm going to switch over here, guys, and we're going to get 13 minus 5 is 8 equals, and those cancel, 4a, and then we'll divide both sides by 4 and get a is equal to 2. So remember, this is what an equation in vertex form should look like. We had better know the values of 3 things in order to do it. H and K, which we already knew, and A. So I'm going to rewrite this right over here, guys, but with values put in here, and here, and here. But the X and the Y remain in the original equation. So it's going to be Y equals, our A value we just came up with is 2. Then in parentheses, the X stays, minus your H value, which is 3. Close it, square it. And then plus your K value at the end, which in this case is 5. So Y is equal to 2 times X minus 3 quantity squared plus 5. That's the equation of the only parabola out there with a vertex at 3, 5 and containing the point 513 written in vertex form. All right, guys, there's one more example here if you wanted to try that one out on your own, but I'm about out of time right now, so I'm going to wrap this one up. So good luck on the 4.1 homework. Do your best at it and let me know when you have some questions.